leveraging the availability of two cameras for Illuminant estimation. Given a scene under a specific illumination, represented by RGB values, when we image the scene with a camera, the raw image out of the camera sensor will have a color cast caused by the scene illumination. Auto-white balance aims at removing such color cast from images so that colors look more accurate. Auto-white balance is a two-step process. First, we estimate the scene illumination, then we use the estimated illuminant to correct the image. Our method is inspired by the chromogenic color constancy, which involves capturing a normal image and capturing a second image with the same camera while placing a spectral filter in front of the camera, imitating two cameras with different spectral sensitivities. There exists a linear transform, E1, that maps from the first image to the second. If we capture another pair of images under a different illuminant and compute another transform, T2, if the illuminants are different, then the transforms between the image pairs will be different. In other words, the transform T is unique per illuminant. Our method extends the chromogenic color constancy concept to two camera systems in modern smartphones. Such cameras typically have different spectral sensitivities. We capture two images from the two cameras. The images usually have different views, so we warp and crop one of them to match the other. Then we downsample both images to minimize pixel-wise alignment errors. Then we estimate a 3x3 linear transform between the images. Then we use this transform as the only input to a lightweight neural network that estimates the scene illuminant. We use three types of datasets to train and evaluate our method. The first dataset is a radiometric dataset that consists of synthetic image pairs from two cameras. And the second dataset is based on images from two cameras from the NUS color constancy dataset. For the NUS dataset, the images from two cameras have different views, so there is no pixel-wise correspondence to compute an accurate transformation between the images. To solve this problem, we compute a color transformation based on the corresponding color chart values that maps from camera 1 to camera 2. Then we apply this transformation to the image from camera 1 to obtain the corresponding image from camera 2 with pixel-wise correspondence. We collected a third dataset that consists of 156 image pairs captured with two cameras of the Samsung Galaxy S20 Ultra. All images contain the color rendition chart in a fixed location in the images and provided in raw RGB and sRGB color spaces. If we look at the distribution of the ground truth illuminants from the two cameras from each of the three datasets, we can see that the two cameras have different distributions of illuminants, which indicates that they have different spectral sensitivities. The number of images in both NUS and S20 datasets is small, only a couple hundred images in each. To augment these images, we use the following technique. Given two images from the same camera, we extract the color chart values, compute two color transforms from image I to image J and vice versa. Then we use these transforms to re-illuminate the original images so that image I will be re-illuminated by the illuminant from image J and vice versa. We do the same for the corresponding images from camera 2. This process increases the number of training images from M to M squared. Training and testing on the three proposed datasets, our method achieves state-of-the-art performance in terms of mean angular error between estimated and ground truth illuminants. Note that our method uses two images while other methods use one image. However, our method is significantly low light and significantly more efficient. We need only a few hundred parameters to outperform methods that use millions of parameters. We can also see that our data augmentation mechanism gives additional boost in performance. So the take-home message is that using two images instead of one allows us to achieve state-of-the-art performance in illuminant estimation with an extremely lightweight neural network. Most smartphones nowadays have two or more cameras, which makes our method easy to deploy. Thank you. For more details, please scan this QR code.